Take the total mass of everything we can see in the observable universe, every galaxy, every star, every atom of gas and dust across 46 billion light-years in every direction, and plug that number into one of the most fundamental equations in physics. The result is startling. The size you get back, the theoretical boundary that such a mass would create, matches almost exactly the scale of the universe we actually inhabit. That number does not come from philosophy or poetry. It falls directly out of a formula derived from general relativity, and it refuses to be dismissed. Whether that coincidence means something profound about the nature of reality, or whether it is simply a numerical accident with a mundane explanation, is one of the most genuinely unsettling open questions in modern cosmology. To understand why that calculation carries any weight at all, you first need to understand what a black hole actually is, not as a dramatic object from science fiction, but as a mathematical and physical reality. And to do that properly, it helps to understand that the word black hole covers an enormous range of objects, spanning dozens of orders of magnitude in mass, from things smaller than a single atomic nucleus to structures so vast that the concept of size starts to lose its ordinary meaning. Walking through that range from smallest to largest changes your understanding of what a black hole fundamentally is, and prepares you for the genuinely strange territory at the end. Start at the bottom of the scale. In the first fractions of a second after the Big Bang, the universe was not empty and cold and dark. It was extraordinarily hot, extraordinarily dense, and seething with energy in a state that we have no direct experience of and no perfect analogy for. Matter and energy existed in a nearly uniform but not perfectly uniform distribution. Quantum fluctuations, which are not imperfections in some engineering sense, but a fundamental feature of how physics works at small scales, meant that some regions were slightly denser than others. In most of those regions, that density difference was too small to matter. But in some, if the local energy density crossed a critical threshold, something unusual could have happened. The matter in that tiny region could have collapsed directly into a black hole before stars ever formed, before galaxies assembled, before the cosmic microwave background radiation we can still detect today had even cooled into its present form. These are called primordial black holes, and they occupy a strange position in cosmology. They are hypothetical, meaning no confirmed detection of one has ever been made, but they are not physically forbidden. The equations allow them, and in certain inflation models of the early universe, the conditions that would create them arise naturally. What makes primordial black holes genuinely remarkable is their potential size range. Because they formed from density fluctuations in the early universe rather than from dying stars, they were not constrained by the mass thresholds that govern stellar collapse. A primordial black hole could have formed with a mass as small as 10 to the minus 5 grams, which is the Planck mass, the smallest physically meaningful unit of mass. Or it could have formed with a mass equivalent to a large asteroid or a small mountain, compressed into a volume smaller than a proton. Let that physical reality sit for a moment. A black hole containing the mass of 100 million tons, compressed into a space far tinier than any structure you could see with the most powerful electron microscope ever built. If such an object passed through Earth, it would not cause the kind of catastrophe depicted in disaster films. It would not tear the planet apart or trigger earthquakes visible from orbit. It would pass through the Earth almost silently, interacting gravitationally with the matter around it, but for such a brief duration that the effect would be a faint seismic whisper, barely distinguishable from geological noise. The planet would survive. The black hole would continue on its way into interstellar space, detectable, if at all, only by the most sensitive instruments we have ever built. The physics of these small black holes leads to a remarkable prediction first worked out by Stephen Hawking in the 1970s. Every black hole, regardless of size, slowly radiates energy. This is not a classical effect. It cannot be derived from general relativity alone. It emerges from combining quantum mechanics with the curved space-time geometry of a black hole, and the result is a thermal radiation that causes the black hole to lose mass over time. The smaller the black hole, the higher the temperature of this radiation, and the faster the evaporation proceeds. For stellar mass black holes, or supermassive black holes, Hawking radiation is so faint that it is completely undetectable with any instrument we currently have, and the evaporation timescale is so long that it dwarfs the current age of the universe by many orders of magnitude. But for the tiniest primordial black holes, the ones formed with the smallest possible masses, the evaporation would have been complete long ago. Those objects, if they existed, dissolved back into energy in the earliest moments of cosmic history. The ones that formed with slightly larger masses, comparable to an asteroid or a small mountain, have been evaporating for the entire age of the universe. According to calculations, any primordial black hole that formed with an initial mass around 10 to the power of 11 kilograms, which is roughly the mass of a large mountain, would be finishing its evaporation roughly now in the current epoch of cosmic history. The final moments of that evaporation are not subtle. As a black hole loses mass, its temperature increases, which causes it to radiate more intensely, which causes it to lose mass faster, which raises the temperature further. This feedback loop accelerates until the final tiny remnant releases all its remaining mass as an intense burst of gamma rays, an explosion lasting microseconds, but briefly shining with extraordinary energy. The Fermi Gamma Ray Space Telescope, which has been monitoring the sky since 2008, has been searching for exactly this kind of signal. After more than 15 years of observations, no confirmed primordial black hole evaporation event has been detected. This does not prove they do not exist. It places limits on how many of them there might be within our observable range, and on what mass ranges are most plausible. Move up the mass scale by many orders of magnitude, and you reach the black holes, whose existence has been confirmed not once, but thousands of times over. These are the stellar mass black holes, the objects formed from the gravitational collapse of massive stars that have exhausted their nuclear fuel. The physics of their formation involves one of the most beautiful examples of equilibrium and its failure anywhere in nature. A star spends its entire life in a state of dynamic balance. At its core, nuclear fusion reactions convert lighter elements into heavier ones, releasing energy that flows outward. This outward pressure of radiation and hot gas exactly counterbalances the inward pull of the star's own gravity. For billions of years, these two forces hold each other in check, and the star maintains its structure, The fuel changes over time. Hydrogen in the core converts to helium. When the hydrogen is gone, if the star is massive enough, the core contracts, heats up further, and helium begins fusing into carbon and oxygen. This sequence continues up through the periodic table, each stage shorter than the last, until iron accumulates in the core. Iron is where the sequence stops. Unlike every lighter element, iron does not release energy when fused into heavier elements. It absorbs energy. The moment an iron core of sufficient size builds up at the center of a massive star, the outward pressure that has sustained the star for its entire life suddenly disappears. Gravity wins. The core collapses in less than a second, falling inward at a significant fraction of the speed of light. The outer layers of the star, no longer supported, follow the core inward and then rebound off the newly collapsed dense remnant in a shockwave that rips the outer star apart. This is a supernova, one of the most energetic events in the universe. What remains at the center depends on the mass of the collapsing core. If it is less than about twice the mass of the Sun, the matter settles into a neutron star, held up by a quantum mechanical pressure that prevents neutrons from occupying the same quantum state. But if the remnant core mass exceeds roughly 2 to 3 solar masses, not even that quantum pressure is sufficient. The collapse continues. There is nothing left to stop it. The matter compresses into a region so small and so dense that it vanishes behind an event horizon, a boundary in space beyond which the escape velocity exceeds the speed of light. A stellar mass black hole has formed. The typical mass of these objects ranges from a few times the mass of the Sun to perhaps 50 or 60. Solar masses, for the heaviest ones, formed from single star collapses. Estimates suggest that tens of millions of stellar mass black holes exist in the Milky Way alone. Nearly all of them are invisible. A black hole with no nearby matter to interact with simply sits in space, bending the light that passes near it, but producing no light of its own. We detect them only when circumstances conspire to make them visible. If a stellar mass black hole orbits a normal companion star, it can strip gas from that companion, pulling it into an accretion disk that glows brilliantly in X-rays as the gas spirals inward and heats up. Hundreds of these X-ray binary systems have been identified. In some cases, the orbits and velocities of the companion stars can be measured precisely enough to calculate the mass of the invisible object with confidence, confirming that it is too massive to be a neutron star. The other major detection method arrived in 2015, and it transformed astrophysics. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected its first gravitational wave signal, a tiny distortion in the fabric of space-time produced by two black holes merging far from Earth. The signal lasted only a fraction of a second at the detector, but the analysis revealed the event it encoded. Two black holes of approximately 36 and 29 solar masses had been orbiting each other for millions of years, spiraling gradually inward as they radiated gravitational energy. In the final fraction of a second before merger, they released an amount of energy equivalent to 3 solar masses entirely in the form of gravitational waves. The remnant black hole had a mass of about 62 solar masses. 3 suns' worth of mass had converted to gravitational radiation in less than a second. Since that first detection, gravitational wave astronomy has matured rapidly. Dozens of merger events have been confirmed, and the catalog of black hole masses has grown substantially. These detections have also revealed something unexpected. Some of the black holes involved in gravitational wave mergers have masses in ranges that were thought to be difficult or impossible to produce through standard stellar evolution. The pair instability mass gap, a range of roughly 100 to 140 solar masses, was predicted to be largely empty because stars in that mass range do not collapse smoothly. The physics involves a process called pair instability. In the core of an extremely massive star, at temperatures exceeding a certain threshold, photons can spontaneously convert into electron-positron pairs, particle-type-conical combinations that carry away energy without contributing to the outward pressure the star needs to maintain its structure. When this happens in a stellar core, the pressure drops, the core contracts, temperatures rise further, and the rate of pair production accelerates. This can trigger a catastrophic runaway thermonuclear explosion that obliterates the entire star, leaving no compact remnant at all. 4 stars massive enough to encounter this fate. The result is not a black hole, but a complete dispersal of the stellar material into space. This creates a predicted gap in the black hole mass function. Black holes formed from single collapsing stars should be rare or absent in the range, from roughly 50 to roughly 140 solar masses. The first compelling gravitational wave event to challenge this picture arrived in May of 2019. The signal, catalogued as GW19521, originated from the merger of 2 black holes with masses of approximately 85 and 66 solar masses. The 85 solar mass object sits squarely in the region where standard stellar evolution predicts black holes should not easily form. The most likely explanation involves mergers of smaller black holes that had already combined in dense stellar environments, building up mass incrementally until they reached the pair instability range. This hierarchical merger channel, where each generation of mergers produces more massive black holes than the last, may be responsible for populating the mass ranges that single-star collapse cannot easily reach. The GW19521 merger itself produced a remnant of about 142 solar masses, which places it at the lower boundary of the intermediate black hole range, a region that had remained largely observationally empty for decades. Gap between stellar mass black holes and the monsters at the centers of galaxies remained one of the more puzzling features of the black hole mass spectrum for years. Objects in the range from a few hundred to a few tens of thousands of solar masses were predicted to exist on theoretical grounds, but convincing detections were frustratingly rare. This is partly because intermediate mass black holes do not fit neatly into the environments where black holes usually make themselves visible. They are too massive for the typical X-ray binary systems that reveal stellar mass black holes, but too small to power the spectacular nuclear activity that makes supermassive black holes detectable. Distances. Candidate intermediate black holes have been found in the centers of globular clusters, the tightly packed spherical collections of old stars that orbit galaxies. Some globular clusters show stellar motions, near their centers that are better explained by a central massive dark object than by any distribution of ordinary stars. The masses inferred from these stellar kinematics sometimes fall in the intermediate range, but converting a stellar velocity dispersion measurement into a confident black hole mass requires assumptions about the cluster structure that are hard to verify independently, and debates about specific candidates have persisted for years. More recently, gravitational wave observations have provided cleaner evidence. The intermediate mass remnant produced in the GW195-21 merger, and additional hints in other events, suggests that the intermediate regime is populated, though perhaps sparsely, and that mergers in dense star clusters are a plausible formation pathway. Whether a significant population of isolated intermediate mass black holes exists in galactic halos, or whether they congregate preferentially in stellar clusters, remains an active area of research. Future gravitational wave detectors with improved sensitivity at lower frequencies, such as the proposed laser interferometer space antenna, which is planned to be a space-based detector sensitive to much lower frequency gravitational waves than LIGO, should be able to detect intermediate black hole mergers directly and begin building a statistical picture of this mass range. The supermassive black holes at the centers of galaxies occupy a completely different conceptual category. While stellar mass and intermediate mass black holes are objects embedded in larger structures, supermassive black holes appear to be defining features of their host galaxies, intricately linked to the formation and evolution of the galaxy as a whole. The mass range of confirmed supermassive black holes spans an enormous range. The smallest known supermassive black holes have masses of perhaps 100,000 solar masses. The most massive approach tens of billions of solar masses. Our own galaxy's central black hole, named Sagittarius A star, sits at around 4 million solar masses. Sagittarius A star was not directly imaged until 2022, but its existence and mass were established decades earlier through a different and remarkably elegant method. The center of the Milky Way is obscured by enormous clouds of gas and dust that block visible light completely. Radio waves and infrared radiation can penetrate this obscuring material. However, and telescopes operating at these wavelengths have been tracking the motions of individual stars near the galactic center for more than 30 years. The stars closest to the center move extraordinarily fast. One of them, designated Eastu, travels at speeds of up to 24 million kilometers per hour on an orbital path that brings it within a few light hours of the galactic center at closest approach, applying the same orbital mechanics used to calculate the masses of planets in our solar system, but scaled up enormously. Astronomers can determine the mass of the unseen object these stars are orbiting. The orbital parameters of East-2 and dozens of other stars near the galactic center all converge on the same answer: a mass of approximately 4 million solar masses concentrated in a region too small to be any known class of astronomical object other than a black hole. The alternative explanations have all been ruled out one by one. A dense cluster of dark objects would eventually disrupt the tight stellar orbits being observed. Any other compact configuration would have been gravitationally unstable over the timescales involved. A black hole is the only explanation consistent with all the observations. The direct imaging by the Event Horizon Telescope collaboration confirmed the picture. This project linked radio telescopes on multiple continents, including sites in Hawaii, Chile, Arizona, Spain, Greenland, and the South Pole, into an effective aperture as large as Earth itself. In 2019, this network produced the first direct image of a black hole shadow, the dark silhouette of the black hole at the center of the M87 galaxy, surrounded by a bright ring of superheated plasma following curved paths around the event horizon. In 2022, the same collaboration released an image of Sagittarius, a star, the first direct image of our own galaxy's central black hole. Both images showed the characteristic ring-shadow structure predicted by general relativity, providing powerful confirmation of the theory in an extreme gravitational regime. The supermassive black hole in M87 is substantially more massive than Sagittarius Aster. Its mass is approximately 6.5 billion solar masses, making its event horizon large enough to contain our entire solar system with room to spare. And M87's black hole is not particularly exceptional by the standards of the most massive galaxies. Active galactic nuclei powered by supermassive black holes, consuming matter at high rates, can be among the most luminous objects in the universe, and the black holes powering the brightest of them exceed Sagittarius, a star, by factors of thousands. Relationship between supermassive black holes and their host galaxies is one of the more intriguing puzzles of modern astrophysics. Observational studies over the past few decades have revealed a striking correlation. The mass of the supermassive black hole at the center of a galaxy scales with the mass of the galaxy's central bulge, the dense spherical component of stars surrounding the nucleus. This relationship is tight enough to allow the black hole mass to be estimated from measurements of the surrounding stellar population. It holds across an enormous range of galaxy types and masses. From modest spiral galaxies to massive ellipticals, this correlation implies that black holes and their host galaxies growing together over cosmic time through processes that linked the mass growth of the central black hole to the mass growth of the surrounding stellar population. The mechanism of this coevolution is not fully understood. One leading idea involves feedback. When a supermassive black hole is actively accreting matter, the energy it releases can drive powerful outflows of gas that sweep through the host galaxy, suppressing star formation and regulating the supply of new material available for both the black hole and new stars to consume. This feedback loop creates a self-regulating system where the black hole's growth and the galaxy's growth are intertwined. The details of how this works across different redshifts and galaxy types are still being worked out, and different theoretical models make different predictions that future surveys will test. Beyond the supermassive black holes found at the centers of ordinary galaxies lies a regime of objects so extreme that the term supermassive starts to feel inadequate. The most massive black holes known, sometimes called ultramassive black holes, carry masses of tens of billions of solar masses. These objects power the brightest quasars, the intensely luminous cores of distant active galaxies that were observed in large numbers when astronomers first surveyed the sky at radio wavelengths in the middle of the 20th century and initially appeared to be peculiar stars rather than galactic nuclei. One of the most massive black hole candidates known is the object powering the quasar ton. The light arriving at our telescopes from this object has been traveling for over 10 billion years, meaning we see it as it was when the universe was only a few billion years old. The estimated mass of this black hole falls in the range of tens of billions of solar masses, though the exact figure depends on modeling assumptions, and different methods of estimation give somewhat different results. What is not in dispute is the extraordinary brightness of the quasar it powers. The accretion disk surrounding this black hole releases enough energy to outshine hundreds of trillions of stars simultaneously. The host galaxy is nearly invisible behind its own nucleus. The existence of ultramassive black holes in the early universe creates a significant theoretical challenge. There is a physical limit on how fast a black hole can grow through accretion. If a black hole consumes matter too rapidly, the radiation produced by the superheated infalling gas becomes so intense that its pressure pushes outgoing gas away more strongly than gravity pulls new gas inward. This Eddington limit, named for the British astrophysicist Arthur Eddington, who first derived it in the early 20th century, sets a rough ceiling on the accretion rate relative to the black hole mass. A black hole accreting at exactly the Eddington rate grows exponentially, but the timescale for that exponential growth is tens of millions of years. Growing a black hole from stellar mass to tens of billions of solar masses in the few billion years available in the early universe. Starting from a seed of only a few tens of solar masses and accreting at the Eddington rate would not leave enough time to explain the existence of ultramassive black holes in the early universe. Theorists have proposed several alternatives to the standard picture. One possibility is that the first black holes in the universe were not formed from stellar collapse at all, but from the direct gravitational collapse of enormous primordial gas clouds, which could have produced seeds with initial masses of hundreds of thousands or even millions of solar masses, dramatically shortening the time needed to grow to ultramassive scales. Another possibility is that accretion can proceed at rates significantly above the Eddington limit for sustained periods, a process called super-Eddington accretion, in which the infalling matter arrives so quickly that the radiation cannot escape efficiently and the standard feedback mechanism breaks down. Evidence for super-Eddington accretion has been found in some nearby active galactic nuclei, and the chaotic environment of the early universe may have provided especially favorable conditions for it. A third possibility involves the merger history. If multiple massive black holes assembled in a dense protogalactic environment and merged repeatedly, the combined mass of the merger products could have reached ultramassive scales more quickly than any single accretion episode could achieve. In practice, the observed ultramassive black holes probably grew through some combination of all three processes, with the relative importance of each varying depending on the specific history of each object and its environment. Future observations with instruments like the James Webb Space Telescope, which can detect the earliest galaxies and quasars at redshifts greater than 10, corresponding to times when the universe was less than 500 million years old, are providing new constraints on when and how these extreme objects first appeared, beyond even the ultramassive black holes confirmed by observation. Theoretical physics allows for objects that would dwarf ton 618 by enormous factors. These hypothetical objects, sometimes given the informal designation of stupendously large black holes in the scientific literature, are defined as having masses exceeding 100 billion solar masses, and in principle, the mass scale could extend indefinitely higher. No confirmed detection of an object in this range has been made. Their existence is not ruled out by physics, but their formation would require circumstances even more extreme than those invoked to explain ultramassive black holes. If stupendously large black holes exist, they would be gravitationally dominant on scales comparable to galaxy clusters. A single such object could influence the motion of thousands of galaxies and their constituent hundreds of billions of stars across a region spanning hundreds of millions of light-years. Their tidal fields would stretch and distort the large-scale structure of the universe in ways that should, in principle, leave observable signatures in the distribution of galaxies and in the detailed structure of the cosmic microwave background, the faint thermal radiation left over from the early universe. The fact that such signatures have not been conclusively detected places real constraints on how many such objects could exist and how massive they could be, even if they have not been individually observed. Some theoretical models have proposed that a small fraction of the dark matter, the invisible mass component that makes up most of the matter content of the universe, might consist of very massive primordial black holes, including potentially objects in the stupendously large range. This is an intriguing idea because dark matter remains one of the most significant unsolved problems in physics. Decades of observations have confirmed that some form of invisible mass is responsible for holding galaxies together and for the pattern of structure in the universe. But the particle nature of dark matter, if it is a particle at all, has not been determined. The hypothesis that some dark matter might be made of primordial black holes has waxed and waned in popularity over the years. Current constraints from gravitational lensing surveys, from the cosmic microwave background, and from the dynamics of small galaxies have ruled out primordial black holes as the dominant component of dark matter across most of the mass range. But windows remain open in certain mass ranges, and the question is still being actively explored. The entire hierarchy of black holes, from the hypothetical primordial objects tinier than protons to the ultramassive monsters at the centers of the largest galaxies and beyond, has been characterized so far in terms of specific masses and sizes. But the final step in this hierarchy requires abandoning the intuitive assumption that all black holes are extremely dense objects, because the density of a black hole, properly understood, does not have to be extreme at all. The Schwarzschild radius, derived by Carl Schwarzschild from Einstein's general relativity equations in 1916, gives the size of the event horizon for a non-rotating black hole of a given mass. The formula is straightforward. The Schwarzschild radius equals 2 times Newton's gravitational constant times the mass, divided by the square of the speed of light. For the mass of our Sun, this gives a Schwarzschild radius of about 3 kilometers. For the mass of Earth, it gives about 9 millimeters. These are extraordinarily small radii relative to the masses involved, which is why stellar mass black holes are extremely dense objects. If you compressed the Sun to a sphere 3 kilometers across, the average density would be fantastically high. But the Schwarzschild radius scales linearly with mass. If you double the mass, you double the radius. The volume of a sphere scales as the cube of the radius. So the average density of a black hole scales inversely with the square of its mass. Make the mass 10 times larger, and the average density drops by a factor of 100. Make the mass 1,000,000 times larger, and the average density drops by a factor of 1 trillion. This is not a subtle correction. It is a dramatic change. For a supermassive black hole with a mass of 1 billion solar masses, the average density inside the event horizon is already lower than the density of water. For an ultramassive black hole of tens of billions of solar masses, the average density inside the event horizon is comparable to the density of air. And for a hypothetical black hole with a mass of roughly 6 times 10 to the 22 solar masses, which is the approximate mass of the observable universe in conventional matter, the Schwarzschild radius would be approximately 46 billion light-year, which matches almost exactly the current estimated size of the observable universe. The average density of such an object would be approximately 10 to the minus 29 grams per cubic centimeter, which is comparable by order of magnitude to the current average density of matter in the observable universe. These numbers are not being stretched or massaged. They follow directly from the definitions and from the known values of cosmological parameters. The observable universe has a mass. That mass has a Schwarzschild radius, and that radius matches the distance to the cosmic horizon. The average density of the corresponding hypothetical black hole matches the average density of the cosmos. What do physicists make of this? The honest answer is that there is no consensus, and the range of interpretations spans from the mundane to the philosophically radical. At one end of the spectrum, some cosmologists point out that the coincidence is less surprising than it appears. The Friedmann equations of general relativity, which describe the expansion of the universe, and the Schwarzschild solution, which describes a black hole. Both derive from the same underlying theory. Certain dimensionless combinations of cosmological parameters are naturally of order unity in any universe that has been expanding for a long time, and the apparent coincidence between the Schwarzschild radius and the cosmic horizon may simply reflect this. The Hubble radius, which is the distance corresponding to the point at which the recession velocity of galaxies due to cosmic expansion equals the speed of light, is closely related to the Schwarzschild radius of the observable universe's mass. This connection exists in any Friedmann-Robertson-Walker cosmology, regardless of the specific values of the cosmological parameters, which suggests it may be a structural feature of the equations rather than a meaningful physical statement about the universe being a black hole. At the other end of the spectrum are theoretical proposals that take the coincidence seriously as a physical fact requiring explanation. There are mathematical models developed within the framework of general relativity and extended with various assumptions about quantum gravitational effects, in which our universe could be understood as the interior of a black hole in a larger, higher dimensional spacetime. In these scenarios, The Big Bang corresponds not to a creation event, but to the formation of a black hole from the perspective of an external observer in the parent universe. The expansion of our universe corresponds to the expansion of the interior region of the black hole as it forms the cosmic horizon, the surface beyond which we cannot receive signals because the universe is expanding too fast for light from those regions to ever reach us, corresponds to the event horizon. These ideas were explored seriously by several physicists in the 1990s and 2000s. Lee Smolin, a physicist at the Perimeter Institute, developed a framework he called cosmological natural selection, in which black holes in each universe give birth to new universes with slightly different physical constants. And the most common universes would be those with physical constants optimized for producing black holes. This is a speculative but mathematically coherent proposal that makes some empirical predictions, including predictions about which parameter values should be most common across universes, though testing those predictions directly is obviously not possible. Nikodem Poplawski, a physicist at the University of New Haven, has developed models using Einstein-Cartan theory, an extension of general relativity that includes the effects of matter's quantum spin on space-time geometry, in which the interior of every black hole contains a new universe. In these models, the torsion generated by infalling spinning matter creates a repulsive, gravitational effect at extreme densities that halts the collapse before a singularity forms, and the subsequent bounce creates an expanding interior that looks, from inside, like a Big Bang. These are serious calculations in a serious theoretical framework, even if their connection to our actual universe remains speculative. What makes all of these ideas genuinely interesting from a scientific standpoint, rather than merely philosophically entertaining, is that they make contact with real observational questions. If our universe formed inside a black hole in a parent universe, certain features of our cosmology might carry signatures of that formation event. The statistical properties of the cosmic microwave background, the distribution of matter on the largest scales, the values of fundamental constants, these all constrain what any viable cosmological model must explain. General statements about universes inside black holes are not automatically consistent with everything we observe, and the process of checking consistency disciplines the theoretical speculation into something more concrete. At the same time, there are formidable obstacles to taking these ideas too literally. The event horizon of a black hole is defined relative to observers in the exterior spacetime. If we are inside a black hole, we have no access to the exterior. We cannot, even in principle, observe the parent universe or confirm that a horizon exists from the other side. The mathematical equivalence between the Schwarzschild interior geometry and an expanding cosmological metric is real. But equivalence in mathematical structure does not automatically imply physical identity. The equations of fluid dynamics and the equations describing traffic flow share certain mathematical structures. But water and cars are not the same thing. There is also the question of what happens at the singularity. Classical general relativity predicts that a collapsing black hole forms a singularity, a point of infinite density where the equations break down. If our universe formed from a black hole collapse, the Big Bang singularity and the black hole singularity might be related. But the nature of that relationship requires a theory of quantum gravity to to spell out properly, and no such theory is yet complete. Loop quantum gravity and string theory both suggest that quantum effects prevent the formation of true singularities, replacing them with finite density bounce events. But the specific predictions depend on details of the theory that are not yet settled. What remains undeniably true, after all the caveats and qualifications, is that the numerical coincidence at the heart of this discussion is real. The mass of the observable universe, converted through the Schwarzschild formula, gives a radius that matches the observable universe. This connection does not arise from fine-tuning or careful parameter selection. It emerges from the physics as written. Any good scientific question that follows from a real numerical coincidence deserves to be asked. And the question of what, if anything, that coincidence means for our understanding of cosmology deserves to remain on the research agenda. The relationship between black holes and cosmology runs deeper still. The thermodynamic properties of black holes, developed in the 1970s and 1980s by Hawking, Jacob Bekenstein, and others, revealed that black holes have an entropy proportional to the area of their event horizon, not their volume. This area-entropy relationship was the first concrete hint that quantum gravity might organize information very differently than classical physics suggests. It eventually led to the holographic principle, the idea that the information content of any region of space is encoded not in the three-dimensional volume but on the two-dimensional boundary surface surrounding it. The holographic principle, in turn, has led to the AD-CFT correspondence, a precise mathematical duality discovered by Juan Mendocino, 97, in which a theory of quantum gravity in a certain type of negatively curved space is exactly equivalent to a quantum field theory, without gravity living on the boundary of that space. This correspondence has been one of the most productive ideas in theoretical physics over the past 3 decades, generating thousands of papers and providing new tools for understanding strongly coupled quantum systems and contexts ranging from quark-gluon plasma to condensed matter physics. It also raises the possibility that our own universe, if it is, in some sense, enclosed by a horizon, might have a holographic description in terms of a lower dimensional theory on that boundary. These ideas are not settled science. They are theoretical frameworks that are actively being developed and tested in various limited contexts, but they illustrate how seriously physicists take the relationship between black holes and the large-scale structure of reality, and why the apparent numerical coincidence between the Schwarzschild radius of the observable universe's mass and the actual size of the observable universe is taken seriously as a potential clue rather than dismissed as coincidence. The observational program that will shed most light on these questions in the coming decades involves mapping the universe with unprecedented precision. The Vera Rubin Observatory in Chile, which began science operations in 2025, will photograph the entire southern sky repeatedly over 10 years, producing a dataset of billions of galaxies whose positions, shapes, and motions encode information about dark matter, dark energy, and the large-scale structure of the cosmos. The Euclid satellite, launched in 2023, is conducting a wide-field survey in optical and near-infrared light designed to measure the geometry of the universe and the growth of structure with unprecedented precision. The square-kilometer array when fully operational, will observe the universe in radio waves with a collecting area far exceeding any existing telescope, enabling studies of hydrogen gas across cosmic time and mapping the large-scale structure of the universe in 3 dimensions. These surveys will not directly tell us whether we live inside a black hole, but they will place increasingly tight constraints on the geometry of the universe, the distribution of matter and energy, and the consistency of the standard cosmological model. Any significant deviation from the predictions of standard cosmology would be a strong motivation to look for alternative explanations, including ideas that take seriously the relationship between black holes and cosmological structure. Conversely, continued precision confirmation of the standard model would narrow the range of viable alternative frameworks. At the same time, gravitational wave astronomy will continue to expand our census of the black hole population across the universe. The LISA mission, if it proceeds as planned, will detect gravitational waves at frequencies much lower than LIGO can access, opening up a new window on massive black hole mergers, including the kinds of mergers that built up the ultramassive black holes at the centers of the largest galaxies. The Einstein telescope and Cosmic Explorer, proposed next-generation gravitational wave detectors significantly more sensitive than current instruments, would be able to detect stellar mass black hole mergers across nearly the entire observable universe, providing a statistical picture of how black hole populations evolved over cosmic time. Perhaps most significantly for the questions raised in this discussion, the next generation of very long baseline interferometry arrays, building on the Event Horizon Telescope, will produce sharper images of black hole shadows and potentially resolve the structure of their immediately surrounding regions at scales comparable to the event horizon itself. These observations test general relativity in the strongest known gravitational fields and constrain models of what happens near a singularity. If the physics near a black hole differs from the predictions of classical general relativity in ways that reveal quantum gravitational effects, those deviations would be profound evidence about the nature of spacetime at the most fundamental level. We began this exploration at the smallest conceivable scale, with hypothetical black holes smaller than protons and carrying the mass of mountains, potentially scattered throughout the primordial universe by the physics of its first moments. We followed the mass scale upward through the confirmed stellar mass black holes formed in the depths of massive stars, through the intermediate objects whose existence was long suspected and recently confirmed, through the supermassive anchors at the centers of galaxies whose coevolution with their host galaxies remains an active puzzle, to the ultramassive monsters at the extremes of the known black hole population. And then the mathematics itself guided us beyond the range of confirmed observation to a hypothetical scale at which the black hole concept stretches to encompass something as large as the universe itself. What that final step means remains genuinely open. It might mean nothing more than that the equations of general relativity have a certain elegant self-similarity across enormous ranges of scale. It might mean that black holes and expanding cosmological regions are fundamentally the same kind of mathematical object, dressed in different physical language. It might mean that the universe we inhabit is a region carved out inside a larger structure, Or it might mean none of these things, and the numerical coincidence will eventually be explained as a straightforward consequence of cosmological equations, with no deeper implication. It certainly means is that the concept of a black hole is far richer and stranger than its popular image as a swirling vortex devouring nearby material. Black holes are the points where our best theories of space-time are pushed to their limits. They are the objects whose properties first revealed the deep connection between gravity, thermodynamics, and quantum mechanics. They are the subjects of a growing catalog of direct observations that are testing the predictions of general relativity in regimes that were purely hypothetical only a generation ago. And at their largest conceivable scale, they might be the objects that help us understand not just the contents of the universe, but the nature of the boundary that defines what we can know. The study of black holes, from the smallest hypothetical seeds to the largest scales physics can contemplate, is not peripheral to the project of understanding the cosmos. It is one of its central threads. If the questions explored here are the kind that keep you returning to science, please consider subscribing and leaving a comment about which aspect of this story you find most compelling. The relationship between black holes and the structure of the universe as a whole is an area of active research with genuine surprises still to come. And there will be much more to explore as new observations accumulate to fully appreciate the strangeness of the cosmic horizon coincidence. It helps to step back and think about what the Schwarzschild radius formula actually tells us about the nature of gravity. Carl Schwarzschild derived his solution to Einstein's field equations while serving in the German military during World War I, transmitting his calculation from the Russian front in 1916, just months after Einstein published the general theory of relativity. Einstein himself was surprised by the elegance and completeness of the solution. The Schwarzschild metric describes the geometry of spacetime around any spherically symmetric mass, and it works with remarkable accuracy across an enormous range of scales, from the slight bending of starlight around the sun, confirmed during the solar eclipse of 1919, to the orbital dynamics of stars within a fraction of a light-year of the galactic center. The formula has been tested in environments spanning many orders of magnitude in gravitational field strength, and it has not failed yet. What the formula gives you is a length scale. For any mass, there is a corresponding Schwarzschild radius, and that radius tells you what size an object of that mass would need to be compressed to in order for its escape velocity to reach the speed of light. For ordinary objects, this size is fantastically small. The Earth would need to be compressed to the size of a marble. The Sun would need to be compressed to a sphere about 3 kilometers across. But because the formula scales linearly with mass rather than with volume, and because volume grows as the cube of radius, the density required to reach the event horizon scale decreases as the mass increases. For large enough masses, the density required is not exotic at all. This is a point worth dwelling on because it challenges the intuitive picture of a black hole as something exceptionally dense and compact. In the popular imagination, a black hole is a point of infinite density, or at least an object so extraordinarily compressed that it bears no resemblance to ordinary matter. This is true for stellar mass black holes. A black hole with 3 solar masses has a radius of about 9 kilometers, and an average density inside the event horizon that is roughly equivalent to compressing the entire mass of 3 suns into a sphere the size of a small city. That is extraordinary density by any everyday measure. But the concept of an event horizon does not require that kind of density. It requires a specific relationship between mass and size, that the mass be enclosed within the corresponding Schwarzschild radius. For a mass large enough, you can satisfy that requirement at densities lower than water, lower than air, lower than the best vacuum achievable in a laboratory on Earth. A black hole with a mass of about 100 million solar masses has a Schwarzschild radius of roughly 300 million kilometers, somewhat comparable to the Earth-Sun distance. The average density inside this event horizon would be about 1 gram per cubic centimeter, comparable to liquid water. A black hole with the mass of a rich galaxy cluster, perhaps 10 trillion solar masses, would have a Schwarzschild radius of about 30,000 light-years and an average density inside the event horizon of about 10 to the minus 15 grams per cubic centimeter, far lower than the density of air at sea level. You would not feel anything special standing inside such a structure, assuming you could be transported there instantaneously. The tidal forces near the event horizon of such a massive black hole are negligible. You would feel no gravity from the horizon itself, because an event horizon is not a material surface. It is a mathematical boundary defined by the geometry of space-time. This is one of the most counterintuitive features of large black holes. The event horizon is an invisible, intangible boundary. A person crossing the event horizon of a sufficiently massive black hole would not feel anything unusual at the moment of crossing. The local physics would look entirely normal. Clocks would tick at their usual rate. Space would appear flat locally. Light would travel in straight lines to a local observer. The global structure of space-time would be dramatically different, in the sense that the crossing observer could never return to the exterior. But there would be no locally detectable signal of when the crossing occurred. The full consequences would only become apparent much later, as the observer fell deeper into the gravitational field and tidal forces eventually became significant. Local normality of the event horizon crossing is what makes the cosmic horizon coincidence genuinely worth thinking about. If you crossed the event horizon of a very massive black hole without knowing it, and the local physics gave you no direct indication that you had crossed, how would you know? The observable universe has a horizon too, the cosmological event horizon, beyond which light can never reach us due to the accelerating expansion of the universe. We cannot receive signals from beyond that horizon. Observers beyond that horizon cannot receive signals from us. The surface of last scattering, where the cosmic microwave background radiation was released, defines another horizon beyond which we cannot directly observe the state of the universe. These cosmological horizons are not the same as a Schwarzschild event horizon from a mathematical standpoint, but they share the property of being boundaries of observability rather than physical surfaces. The cosmological event horizon in our universe is driven by dark energy, the mysterious component of the universe that is causing its expansion to accelerate. Dark energy was confirmed observationally in 1998 through measurements of type EAA supernova by 2 independent teams. An observation that earned the Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011. Dark energy constitutes approximately 68% of the total energy content of the observable universe, while dark matter makes up roughly 27% and ordinary matter, everything made of atoms, accounts for only about 5%. Despite dark energy dominating the energy budget of the universe, its physical nature is completely unknown. The simplest mathematical description treats it as a cosmological constant, a uniform energy density associated with empty space itself, that was introduced by Einstein in 1917 and then discarded and then rehabilitated by the supernova observations. But whether dark energy is truly constant or varies with time, and what physical mechanism produces it, are open questions with no agreed answer. The accelerating expansion driven by dark energy is what makes our universe's cosmological event horizon permanent. In a universe without dark energy, the expansion would eventually slow and distant galaxies would, in principle, remain reachable given enough time. But in our universe, galaxies beyond a certain distance are receding from us faster than light. Not because anything is moving through space faster than light, which is forbidden, but because the space between us and them is expanding. No signal we send now will ever catch up with those galaxies, and no signal from those galaxies now will ever reach us in the future. This means there are regions of the observable universe that we can currently see because the light from them left before they crossed the event horizon, but which we will lose contact with permanently as time goes on. The observable universe, in the sense of the region from which we can currently detect information, will actually shrink over cosmic time. This creates a strange situation. The cosmic microwave background, which we can observe today, was emitted by matter that is now more than 46 billion light-years away. That matter is beyond our cosmological event horizon, and we can never send a signal to it. What we see when we observe the cosmic microwave background is a snapshot of a surface of last scattering from the early universe, and those locations in space are now unreachable. The observable universe we inhabit is, in a real sense, a bubble of information, and the boundary of that bubble shares certain mathematical properties with the event horizon of a black hole. Understanding dark energy is one of the central challenges of physics in the 21st century. The theoretical prediction for the value of the cosmological constant, based on quantum field theory calculations of the vacuum energy, gives a number approximately 120 orders of magnitude larger than the observed value. This discrepancy between the theoretical prediction and the observed value of dark energy is sometimes called the worst prediction in the history of physics, though characterizing it that way slightly misrepresents the situation. The calculation is not wrong in the sense that no one knows how to do it correctly. The calculation produces a well-defined answer that simply does not match observation by an enormous factor, and no one knows why. This enormous discrepancy is called the cosmological constant problem, and it has resisted solution despite decades of effort by many of the most talented physicists in the world. Some approaches to the cosmological constant problem invoke an anthropic argument. Perhaps the cosmological constant takes many different values in different regions of the universe, or in different universes in a multiverse, and the value we observe is the value compatible with the existence of galaxies, stars, planets, planets, and observers. Steven Weinberg made a specific version of this argument in 19, predicting that the cosmological constant should be small but non-zero, which was confirmed by the supernova observations a decade later. But while this argument correctly predicted the sign and approximate magnitude of the cosmological constant, it does not constitute a physical explanation in the sense of deriving the value from first principles, and many physicists remain unsatisfied with anthropic reasoning as a scientific explanation. The measurement of dark energy and the acceleration of cosmic expansion also ties into the so-called Hubble tension, a currently unresolved discrepancy between different methods of measuring how fast the universe is expanding. The Hubble constant, denoted h0, describes the current expansion rate of the universe, specifically how fast the recession velocity between any 2 points in the universe increases with the distance between them. Measurements based on the cosmic microwave background and the standard cosmological model give a value of approximately 67.4 kilometers per second per megaparsec. Measurements based on calibrated distance ladders using Cepheid variable stars and type Ia supernova in the nearby universe give a consistently higher value, approximately 73 kilometers per second per The difference is about 9%, but the statistical significance of the discrepancy, now well above 4 or 5 standard deviations when multiple independent measurement methods are combined, makes it unlikely to be a simple statistical fluctuation. If the Hubble tension is real and not due to systematic measurement errors, it implies that there is something wrong or incomplete about the standard cosmological model. The fix could involve new physics at early times, such as a component of energy that was present before recombination and has since diluted away, which could shift the early inverse distance scale. It could involve new physics at late times, such as a dark energy that varies over time rather than remaining constant, which would affect how distances are calculated from redshift measurements. Or it could reflect something more fundamental about the relationship between the background cosmological model and local measurements. The James Webb Space Telescope has been contributing to this debate by providing more precise measurements of Cepheid variables in nearby galaxies, and so far its results have generally supported the higher value from distance ladder measurements, making the tension with the cosmic microwave background more difficult to dismiss as a measurement artifact. All of these open questions: the nature of dark energy, the cosmological constant problem, the Hubble tension, the formation mechanism of the most massive black holes, the existence and properties of primordial black holes, connect back to the central theme of this exploration. They all concern the boundary conditions of our knowledge about the universe, the places where our best theories make contact with observations and come up short, where new physics is evidently needed and not yet found. The Schwarzschild radius coincidence sits within this collection of puzzles as an intriguing datum that may turn out to be a deep clue or may turn out to be a structural feature of the equations with no special significance, determining which requires exactly the kind of precision cosmological observations and theoretical advances that are currently under development. One of the more productive recent frameworks for thinking about the relationship between black hole physics and cosmology is black hole thermodynamics, and specifically the question of information. The laws of black hole thermodynamics formulated in the early 1970s, state that the area of a black hole's event horizon never decreases. The black hole has an entropy proportional to its horizon area, and Hawking radiation carries the black hole's energy away over time as thermal radiation. But thermal radiation from a hot object carries no information about what went into the object. A warm oven, when opened, gives off heat that tells you nothing specific about what was cooking inside. If Hawking radiation is similarly information-free, then when a black hole completely evaporates, all information about what fell into it is permanently lost. This black hole information paradox troubled Hawking and many others for decades. The laws of quantum mechanics require that information be conserved. The evolution of a quantum state is unitary, meaning that a given initial state always leads to the same final state, and that process is in principle reversible. If information is destroyed when black holes evaporate, unitarity is violated. This cannot be right from the perspective of quantum mechanics. But how the information escapes from a black hole without violating causality, without anything traveling faster than light, without violating the principles of general relativity near the event horizon, was not clear. The leading current resolution of the information paradox, developed through work by Don Page, Raphael Busso, Juan Maldacena, Ahmed Almhiri, Netta Engel, Henry Maxfield, Jeff Pennington, and others over the past decade, involves subtle quantum gravitational effects that alter the structure of spacetime in the interior of old black holes. The details are technical and involve ideas like quantum extremal surfaces, island contributions to entropy calculations, and replica wormholes. But the broad conclusion of this work is that Hawking radiation does carry information about what fell into the black hole, encoded in subtle quantum correlations between early and late radiation, and that unitarity is preserved. The Page curve, which describes how the entropy of Hawking radiation should change over the lifetime of an evaporating black hole, has been derived in simplified models of black hole evaporation using these techniques, and the result is consistent with unitary evolution. This work has also deepened the connection between black holes and holography. The holographic principle, formalized in the context of ADC-FT, states that the physics inside a gravitational system is fully encoded in a quantum field theory on its boundary. If this is correct, then the interior of a black hole, including whatever happens at the singularity, is completely described by the boundary field theory, and the apparent paradoxes of information loss can be resolved by working in the boundary description, where no gravity is present and unitarity is manifest. The challenge is translating this resolution back into the bulk gravitational description in a way that makes clear physical sense. What does this mean for the idea that our universe might be the interior of a black hole? If the holographic principle applies, then the physics of our universe should be encoded on its boundary, whatever that boundary is. In the standard cosmological model, the universe does not have a boundary in the conventional sense. It might be infinite, or it might be finite, but without an edge, like the surface of a sphere, but in 3 dimensions. But if it has a cosmological event horizon, that horizon might serve as a holographic screen on which the physics of the interior is encoded. This idea has been explored formally by Tom Banks, Willy Fisher, and others under the name holographic cosmology. Though it remains far from a complete theory, the connection between these ideas and the practical observations of the next decade is not always direct. We cannot build a telescope that looks at the holographic boundary of the universe, if such a thing exists. But we can test whether the statistics of the cosmic microwave background are consistent with predictions from holographic cosmological models. We can test whether the large-scale structure of the universe, the network of galaxy filaments and voids that forms the cosmic web, follows the patterns expected from standard inflation versus alternatives. We can search for signatures of a pre-Big Bang phase in the primordial power spectrum of density fluctuations. These observations constrain what happened in the earliest moments of the universe, and therefore, what kinds of initial conditions are consistent with what we see, which is directly relevant to any hypothesis about how the universe began. The cosmic microwave background has been measured with extraordinary precision by the WMAP satellite, which operated from 2001 to 2010, and then by the Planck satellite, which operated from 2009 to 2013. These measurements have determined the basic cosmological parameters: the Hubble constant, the density of matter and dark energy, the amplitude and tilt of primordial density fluctuations, 2% level precision. Future measurements with ground-based telescopes like the Simons Observatory and CMBs-4, which is a proposed next-generation cosmic microwave background experiment involving multiple telescopes across the globe and in Chile specifically, will push this precision significantly further. These experiments will measure the polarization of the cosmic microwave background with high sensitivity, which encodes information about the physics of inflation and about any gravitational waves produced in the early universe. If inflation is correct, the quantum fluctuations during the inflationary phase generated both density fluctuations, which seeded the structure we see today, and gravitational waves, which stretch and compress space in a pattern that imprints a characteristic polarization signal on the cosmic microwave background. The amplitude of this gravitational wave signal depends on the energy scale of inflation, and measuring it would directly tell us how energetic the inflationary phase was, and therefore how close it was to the Planck scale, where quantum gravity becomes important. A detection of this signal would be one of the most significant discoveries in the history of cosmology, providing a direct observational window into physics at energies far beyond what any particle accelerator can reach. All of these threads, the mass hierarchy of black holes, the thermodynamics of event horizons, the holographic principle, the question of information, the precision cosmology of the microwave background, the nature of dark energy and the Hubble tension, connect to the fundamental question of what space-time is and what it is made of at the deepest level. The standard model of particle physics describes matter as built from quantum fields, and general relativity describes gravity as the curvature of a continuous space-time manifold. These two descriptions are individually extraordinarily successful and have never been contradicted by experiment within their respective domains. But they are not compatible with each other in the regime where both should be important, namely at the Planck scale of very small distances and very high energies. The construction of a consistent theory of quantum gravity is the central unsolved problem in fundamental physics, and it is a problem that the study of black holes sits at the heart of. Black holes are the only objects in nature where the effects of both quantum mechanics and general relativity are simultaneously important. For everything else in the universe, either quantum mechanics dominates at small scales and weak gravity, or general relativity dominates at large scales and strong gravity. But at the center of a black hole, where classical general relativity predicts a singularity of infinite density, quantum effects must become dominant. The singularity cannot be physical. Infinite density and infinite curvature are signs that the theory has broken down. Whatever quantum gravity theory eventually replaces, general relativity at the Planck scale will resolve the singularity into something finite, and the nature of that resolution determines what really happens inside a black hole, and potentially what happened at the Big Bang. If the universe formed from the interior of a collapsing region in apparent spacetime, as some models suggest, then understanding what happens at a black hole singularity in quantum gravity terms is not just an academic question about remote astrophysical objects. It is a question about our own origin. The Big Bang singularity that classical cosmology predicts at the beginning of our universe's history would, in this picture, correspond to the singularity of a collapsing region in the parent universe, and the quantum gravitational resolution of that singularity would be what produced the expanding universe we inhabit. The physics at the boundary between the parent universe and our own would be the physics of quantum gravity operating at its most extreme. This is why physicists take seriously the study of black holes at every scale, from the smallest hypothetical primordial objects to the largest conceivable structures at cosmic scales. Each scale offers a different window into the same underlying physics. The gravitational wave observations of stellar mass black hole mergers test general relativity in the strong field regime and constrain the mass distribution of compact objects. The imaging of supermassive black hole shadows tests the geometry of spacetime in the extreme vicinity of event horizons. The thermodynamics of black holes reveals deep connections between gravity, quantum mechanics, and information, and the coincidence between the Schwarzschild radius of the observable universe's mass and the actual scale of the cosmos whispers the possibility that the largest structure we can contemplate might itself be an instance of the same physics. Whether that whisper carries a message or is simply the mathematical echo of a relationship built into the equations of general relativity from the beginning is not yet known. The answer, if there is one, will come not from pure thought but from observation, from the next generation of telescopes mapping the distribution of dark matter and dark energy, from gravitational wave detectors cataloging the merger history of black holes across cosmic time, from precise measurements of the cosmic microwave background probing the physics of the earliest moments, and from theoretical advances in quantum gravity that will eventually replace both general relativity and quantum mechanics with a more complete description. That more complete description, whatever form it takes, will have to account for the fact that the universe we live in has a certain size, a certain mass, and a certain relationship between those two quantities that falls out of one of the most fundamental equations in physics, with no adjustment required.